Good morning, everybody. So this is the third lecture on computable general equilibrium models. Let me start my whiteboard. Okay, I assume that everybody can see it. All right. So last time we okay, there's someone coming. Okay, so we studied existence. We studied uniqueness. Now we're going to look at stability. Okay, so this is today. Remember the Walras law. So the total market value of excess demands is equal to 0, right? And also you should also remember that equilibrium means excess demand in all markets being equal to 0. Okay, so the first thing you see here is a definition of the Walras law. It's the mathematical formulation of the Walras law. And this is the definition of the Walrasian equilibrium. Now, obviously, as we discussed last week, there is this price updating mechanism, right? The Gale-Nicolado mapping. And according to this, if excess demand in a market at some price is positive, then we want the updated price to be larger than the given price, right? The initial price. So we want to impose that property into our discussion of stability, all right? But in the meantime, we know that we have a linearly dependent system, right? So we want to impose a price normalization. Sometimes we do it through the unit simplex, right? As we discussed in existence. So all the prices sum to 1. So this is just one equation that completes our system, right? So that brings new information about prices. And then sometimes we can do other things, right? For instance, this. Now, there are some properties as we discussed last week. So remember that the demand functions are homogeneous of degree 0. This means if all prices increase by the same proportion, then demand does not change. Okay, so now we're going to use this property, all right? We're going to use this property to understand that excess demand functions are also homogeneous of degree 0. Okay, so let me use my notes again. So now suppose that this is the now this is the excess demand in market I, right? So I can identically write this to be more specific about prices in this way, right? So this is the price vector. So as you see, this is any price vector, not necessarily the equilibrium, right? Now, if the demand functions are homogeneous of degree 0, this is true for excess demand function as well. So this is like so there's a mathematical proof, obviously, but in this endowment economy, supplies are fixed, right? So supplies do not change with the prices. So if all prices go up by the same proportion, then basically nothing happens to the demand, so nothing happens to the excess demand. All right. Now then we can do this. So imagine this is our price normalization. All right. Then I can do this. This function zeta I p1 p2 dot 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 pn is identical to, careful, I'm dividing all the prices by p1. Okay. Right? So then I have this. So this is zeta I, by the way. So zeta I 1 p2 dot 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 pn. Now this function, this excess demand function zeta I, has still n arguments, right? But this is just one. So this is identically another function fi p2 dot 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 pn. All right, and this is true for, again, all I. Now, why I'm doing that? Because when I discuss the stability of an equilibrium, in that equilibrium, I basically need to assume a price normalization, and the easiest thing in this setup is to assume that. All right. So then excess demand in market I is expressed as a function of, instead of all prices, now since the first price is normalized to 1, it is expressed as a function of n minus 1 prices. Okay, so here you have n minus 1 price levels. Okay, and again, don't forget, we want fi positive, implying price go up. Okay, so that's also important. Okay, now here is the idea. The question of stability, right? So I'm going to introduce time, okay? Because stability is about time. I want to observe initially an economy that is in equilibrium, okay? So initially, of course, when I write P0, what I mean is, so this is basically time, right? So maybe I can do this. Just a sec. Maybe I can do this. All right. So at time t, the price vector is defined again in this way. Okay. So initially, we are at equilibrium. All right. This is the initial. Now then, I will ask what happens to PT if for some reason at some t, let's say t hat, we are not in equilibrium. All right. So what happens to PT after that point? All right. So you can also imagine this. If this is t, if this is, imagine that there's only one price. All right. So you have this. So this is P star. Then at this t hat, there is a shock for some policy change, some shock. Then economy, let's say, moves to here. All right, so obviously this is not equilibrium. Then we ask whether in time price goes to the equilibrium. All right, this is the stability question in a very, very simple way. So how to study this mathematically? Well, it's very simple. In market I, this is also changing in time, right? Because all prices change in time now. We're going to define this derivative. Okay, so this will be the derivative of this with respect to time. All right, and we will say price in this market grows as a result of changes in excess demand. Right? Now, Ki is some positive constant. Okay? Now, I want you to understand this equation. All right? What does it tell us? Again, since we are discussing stability, now we introduce time. Time here is a continuous variable, as you see, right? It is a continuous variable starting at 0 and extending to positive infinity. Within such a setup, the price vector itself change in time, right? So this is still a price vector, but it change in time. And we define this derivative, okay, the time derivative of price I, price of commodity I at time t. So there is a change. This change is basically expressed in this way, right? D here is for differential. Then I say if excess demand, okay, so this is excess demand. If excess demand in market I is positive, then price change is positive, which means price is going to go up. If this is negative, if excess demand is negative at these prices, careful that this is the entire vector, entire price vector at time t, okay? If this is negative, since excess demand is negative, we want the price go down. All right? So that's our formulation. That's the tool that we're going to use for discussion of stability. Now, obviously, there is K1, K2, okay, K3, ... Kn. All right, in all markets, there's that. But careful with one thing, since we normalized for commodity I, since price is always equal to 1, I actually don't have this type of an equation for this market, right? Because P1 T is always equal to 1. All right, this is true for all episodes. So I have actually n-1 differential equations. Okay. So the idea will be to use this equation. This is a differential equation, so I can discuss the ideas of existence, uniqueness, and stability through this equation. All right. Now let me be a little bit more specific about dimensions. So P1 dot T is always equal to 0. Why? Because P1 t is equal to 1 for all t. Okay, then I have p2 dot t. p2 dot t is k2 f2 p2 dot 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 pn, right? Then I have p3 t, which is k3 f3 p2 dot 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 pn. All right. So finally, I have pn dot t, which is kn fn p2 dot 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 pn. All right. So now how can I define equilibrium? Careful. K2 is greater than 0, K3 is greater than 0, dot, 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 Kn is greater than 0. So the equilibrium is defined in this way, right? If Pi dot T is equal to 0, then this is equilibrium. Okay? Because equilibrium requires these F's to be 0, right? These are excess demands. These are excess demands. So in equilibrium, they're equal to 0. Okay? So we have now n minus 1 dimensions, as you see. Okay? N minus 1 differential equations. Okay. Now, what we can do is this. Now, we want to rewrite this system in this way. I'm looking at your note. So, by the way, this is not from your textbook. This is from another book. But I am simplifying the matters a lot. Okay. So you don't need to check the text, and I mean, you don't need to go back. So remember, you have n minus 1 equations now. So this is a vector, okay, whose dimension is n minus 1 times 1. Okay, so it's a column vector. Now this is n minus 1 by n minus 1. So it is a matrix. Okay, this matrix looks like that. K2 0 dot 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 0 0 K3 dot 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 0 dot 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 0 Kn. As you see, it's a diagonal matrix. Okay, it's a diagonal matrix. Now this, on the other hand, is still a vector, right? And its dimension is n minus 1 by 1. Okay. So this is the same thing that I just showed you, this one, this thing. All right. Same stuff. Okay. You can still see my screen, right? Everybody, do you see my screen?
Yes.
Yeah.
Okay, good. Now, let me define, so we didn't talk about what K means, right? So I have P dot T K F of PT. So here, each K is the speed of adjustment parameter. Speed of adjustment. in the sense that if this parameter is high, then convergence to the equilibrium is faster. Okay? Okay? Convergence to the equilibrium is faster. Now, here is the, you will have, of course, theorems. Now, here is one of the theorems that we are going to focus on for stability. Okay, so this is from Arrow, Hurwitz, Arrow, Block, and Hurwitz. 1959. Okay, it goes like this. P star is asymptotically globally stable, okay, for P dot equals K FP, if and only if, sorry, no, not if and only if now I will explain what this is, but this is your global stability theorem. Okay? Now, what do we have here? Now, these orders basically show us that for equilibrium to be globally stable, globally in the sense that it is true for all P, okay, so globally means it is true for all P, all right? If this derivative is positive, and this derivative must be positive for all commodity pairs, okay? All commodity pairs. So what does this mean? What's the economic meaning of this derivative? Can somebody explain? Remember, F is excess demand and P is price. Now, I'm looking at market I, right? So this is excess demand in market I, and I say excess demand in market I should be positively changing with the price of commodity J. What does it mean? Think about it. There is a very simple and specific economic intuition here. People, it's very simple.
Maybe I'm wrong. I guess there is difference between supply and demand.
Okay, so here is the idea. So demand is there, chi parameter, right? Chi function. So you have prices, you have endowments. Everybody has a demand. Then we have total market demand, right? Total market demand minus total market supply of this good is your excess demand, right? Now, excess demand depends on not the price in that market, but all the other prices, right? Now, I'm telling you in this derivative that excess demand in market I, let's say we are in the lemonade market, okay? in the lemonade market, I'm looking at the effects of the price of Coca-Cola. All right? And I require, if the price of Coca-Cola increases, excess demand in the lemonade market should increase. What does this mean?
Complementary goods.
No, exactly the reverse. They should be substitutes, right?
Sorry.
They should be substitutes. Because if the price of Coca-Cola increases, I transfer my demand from Coca-Cola to lemonade, right? So this derivative tells you commodity I and commodity J should be substitutes. Okay? But it requires something very strongly, right? It requires something actually very strong. This must be true for all commodities. Okay? This must be true for all commodities in the economy. And again, this is the global stability, so it must be true in each price. What does this mean? Imagine the demand function. So imagine the market here. So this is Q, this is P, there is some demand function, right? So the relationships must be true for the entire domain of prices. Okay? This is usually a very strong assumption. So we require all commodity pairs to be substitutes. And this must be true for global stability. Okay, global stability must be true for all P. All right, so this is your theorem, one of the theorems on stability. In this version we have global stability. Okay. Now we have less than a minute. My time is almost 9:40. I think the video. Oh, okay. So the video will take about 15-minute conversion. So let's meet at 9:55. Is that good for everybody?
Yes.
Okay,
Yes.
good. And think about this theorem, all right? While you are drinking your tea or coffee, think about the meaning and stringency of this thing. It's high. It's very strong. The assumption, the if condition that guarantees stability is a very strong condition. So think about this. We're gonna return with a slightly less stringent version, another theorem, and then we're gonna continue at 9:55. Okay. I see you in 9:55.